The problems that you guys had to do last night. Number 2 was the first one. You had to find the particular solution of that. So you should have gotten um, y equals square root of x squared minus 16. So the general solution, you would have gotten the plus and the minus, and then solving for the c, you would end up getting looks like negative 16 with a positive one since we had a positive initial condition. You gonna go with that? Number 7, which one corresponded to the slope field? And you should have gotten for that one D. D as in dog. Do we need any explanation on that? So notice a couple things here on this. Um, these are all zeros here. That's because where x is 0, so that would make sense. That works for all of them, though. All right. There's also this gap here. This is probably the biggest indication, the gap there at y equals negative 2, which says that it's undefined. And if you plug negative 2 into here, it would make it undefined, so then it kind of narrows it down to those two. And then from that point, so you can eliminate these two. This one's squared and this one's cubed, so I would look at like a negative x value and basically see what the result is. Because if it's a negative and it's positive, then that tells you to be this one, and if it's a negative and it's negative, that would be that one. So you can see here like negative 1, 1, like that. If you plug that in, well, it's a negative slope, which wouldn't make sense because this one is. So this one would not be able to become positive in square. That's how it would be. And then the other one was number 10. Which of these was a solution to the differential equation? So the way to do that is to find the derivative of each one and plug that basically in. So you, for example, the first one, you would do y prime is e to the x minus 2 e to the negative x would be the derivative. And then so you basically plug that into the equation, e to the x minus 2 e to the negative x, plus the original equation, e to the x plus 2 e to the negative x. And does that equal e to the x? And these cancel, these cancel, these do not. It gives you 2 e to the x, so that's not. And you just got to work your way down and see what the answer would be. Do all those 10. There it says not a solution. A, so B was a solution, and then C is not, and D is not. B was the solution. Do we do okay with that? Okay, and then that was it. Right, those 3. So we'll start in at number 8. This one, the reason that I skipped it is because it looked a little different, a little bit challenging. So we haven't talked about concavity for a while, so just kind of throws that in this middle of a review for other stuff. So it says if the point 2,6 is a point on the solution curve of the differential equation there, determine the concavity of the solution curve at that point. So what do you think of when you think of concavity? Like, second derivative? Yeah, second derivative. So if we're going to figure out something with concavity, we need a second derivative. The confusing thing here is that like you're thinking that you should probably be like integrated or something because it's talking about like solution curves and stuff. But you want to find the second derivative here. That's what we want to do. And also in doing this, probably what I would do is solve for y prime first. You don't necessarily have to, but maybe solve for that first. Just to make it a little bit easier. So if we get the y prime by itself, it would be then 5 minus y over x. Solve for y prime. And that will just make it a little bit easier when we're solving for the second derivative. So then y double prime equals, and this is actually a quotient rule, right? Because remember the quotient rule, it's like derivative of the top times the bottom minus the original top times the derivative of the bottom over the bottom squared. So that's stuck in there. So we got to do the derivative of the top first. So how do we write the derivative of 5 minus y? What's that going to be? What's that for? Yeah, negative y prime. Yes. 5 goes away. The derivative of y is just y prime. All right, and then it's going to be times x, right? Negative y prime x minus 5 minus y times just 1, because the derivative of x is the 1, over x squared. Now there's one other thing we need to do. It gives us a 0.26, but we still got a y prime in there. So then what we do is, since we solved for y prime earlier, is we're going to take this and we're going to plug it back in there for y prime. It ends up being not the most friendly equation here. We got a negative with that too, so negative 5 minus y over x times x. And we'll just go ahead and script that negative minus 5 plus y over x squared. And probably do some simplifying before you plug in. So it looks like when you multiply there, those x's are going to cancel, right? This one should cancel. And then so we get y double prime is negative 5 plus y minus 5 plus y over x squared. You just combine it there. Y double prime is negative 10 plus 2y over x squared. So that would be the form then we would want to plug in the point that it gives us. So then we can plug in the 0.26 for x and y. So 2 times 6 over 2 squared. And then so we get 12 on top. That's times 2, 2 over 4, so we have to positive half. And all we're actually are looking for is the sign that's positive, so this would be conjugated up. It's like a lot of work just to determine what's conjugated up at one point. Mess up one side. It's bad. Yeah.
Well, if you mess up some twice.
That's true, yeah. It'd be good. Alright. Alright, let's do number 9 here. Solve this differential equation for h of t if h of negative 2 equals 3. So we got just a separable differential equation here where we get separation of variables, just different letters, but it works the same. Instead of y's and x's, we just got h's and t's. So we want to get the h's on the left and t's on the right. So let's get h squared dh and t squared dt. Multiply the dt over, multiply the h squared. We can then go ahead and integrate. Get 1/3 h cubed equals 1/3 t cubed And you got a couple options. It doesn't matter any order that you want to do this, but if you want to go ahead and solve for C now, you can. It works at any time. And then solve for the H. Whether you do solve for the H first and then plug in, it really doesn't matter. You can also just multiply everything by 3 if you want to. That makes it easier. Maybe you can do it sort of in an intermediate step. If you want to just multiply everything by 3, you get H cubed equals T cubed plus 3C. Go and do that again, and then plug it in. Now, where if you want to take the cube root, you don't want to have to deal with the cube root as much. You just maybe I'll go ahead and plug in that now. Plug in the initial condition, so we're going to get 3 cubed equals negative 2 cubed plus 3c. So we get 27, and that would become a minus 8, so we have to add it over. We get 35. And so C is out of 3. And then now when we plug it back in, we're going to go up to here. So H cubed is T cubed plus 3 times this, and then the 3's will actually cancel. Right, so probably 3 will multiply by 3. And then so take the cube root, so H of T is the cube root of T cubed plus 35. And again, it's really not hard operations. It's the case with most of these. Not hard integrals, it's just basically following the steps. And again, there's different orders you can do the steps if you want to choose to plug in alpha C here, or if you want to go all the way to this step and alpha C, you can do that. It doesn't matter. Let's do this word problem number 11 here. We got some half-life, we got some CE through the K, so this will be good. The rate of coal production RFT from a coal mine was, that's 2 million tons per year at the beginning of the year 2000. By the beginning of the year 2006, the coal production had decreased to 1,200,000 tons per year. The mine will be profitable until less than 200,000 tons of coal are produced in a given year, assuming that the decline in the amount of coal mined per year closely models the equation for exponential decay. Find the following. A, the particular equation for the amount of coal mined per year, t equals 0 for the beginning of the year 2000. All right, so we got to get a particular solution here, particular equation. Well, I'm not worried about the half-life yet. So let's see what we've got in this. What's some important stuff we've got in this here. Do we know what C is? Yeah, C is 2 million. All right, we don't know what K is, right? It doesn't say anything about the rate. Okay. Now the time, that's something that is generally variable, and we've got some information about that. For the Y, so basically what we're trying to do is trying to write some equation Y equals 2 million e to the something t. Okay. So when we solve this, the y and the t are going to just be y and t for the final, our particular solution. But we need to know what the k is, right? Because it doesn't tell us the k. So in order to get there, we got to use this other information that at the beginning of the year 2006, it decreased to this amount, right? So our equation then will be our y, our new amount, is 1,200,000 equals 2 million e to the, we don't know the k, but in this particular scenario, we know that the t is what? The common mistake is to write 2006 there, just to make sure, like it says the note that t is the beginning of the year 2000. So we're 6 years from the year 2000. So we just need to go ahead and solve for that. So let's do that. Divide 1,200,000 by 2 million. Okay, 0.6, right? And then we want a natural log, and then divide by 6. And then k is going to be the natural log of 0.6 over 6. And if it's a long decimal, we might just want to leave it like that. It doesn't really tell us what to round it to or whatever. So let's try both. 0.085. And then so our particular solution, our particular equation within the y equals 2 million e to the, let's say, negative 0.085. So then this is like our model that we could use for any time. So if we want to know after how many years, say 10 years later in 2010, how much is left, we just plug in 10. If we want to know the year 2022, which right now, see if it's still profitable, probably not. If it's still profitable though. 52 million. Okay, E to 22. Actually, it still is profitable, yeah. Get 308,000. So it's still profitable money. Yeah. I don't have really any idea how mining actually works. Just get like images of like the cartoons with like the train tracks and like the like the parts of like coal in them and stuff. Yeah, with their pickaxe, yeah. But I have no idea what mining's actually like. I guess if you grew up in West Virginia, maybe you would. We do a lot of mining in West Virginia. Okay, the next one is the half-life for the production of coal. So we're supposed to use this to find the half-life. All right, how do we do that? Mm-hmm. Yep. So half-life literally means when it's going to have half the life left, right? So there's a couple ways you could approach it. The easiest way probably is to take this model and think, well, what's the half-life? Well, when's there going to be half of 2 million? Okay. So what's it gonna be in millions? So you just basically plug in a million equals 2 million e to the negative 0.05 t. Then you just solve the t. Always what's going to happen is you're going to divide and you'll just get 0.5. You could also, if you wanted to do, just do c and then 1/2 c. You can do the same thing. So natural law. And then divide. So what do we get?
Um,
8.15, 8.14. Did you, oh, okay, so that's it, no better. Yeah, I don't like that it doesn't tell you how to round here, because you can, yeah, it can change, but I guess we could say approximately 8 years. I think we're just gonna look that, see if that's actually true. I guess coal is made up of different elements, so
I don't think it's really the coal, it's just this,
the particular mine.
yeah, this production rate, how long it'll stay properly.
It says the average lifetime of yeah, I don't know. I guess it depends on what percentage of different elements are in it. I don't know what the elements of coal are, but okay. Next question. Renaissance telling what integral from 0 to 6 of r of t dt from problem 11 represents. So this is a common thing in AP test. Oh yeah, sorry, I guess we just do that. Find the year when it no longer be profitable. So how do we set that up?
When it's zero becomes.
Yeah. Well, not 0, yeah, but 2,000, 200,000. Yeah.
Oh, okay.
Because it won't be profitable once there's less than 200,000 pounds per year. So then what? Yeah, we'll just set equal to 200,000 equals 2 million. E to the negative times 5t. We got about 27 years. So you could imagine, like, if you worked for an energy company, And like, after the first few years, you can like sort of make a model on how much gold you're producing out of the mine. So then like you can like make long-term projections for this company, and this is how many more years we have left in the mine, this 500 years, right? So that they can plan that, we need to find a new mine in the next 5 years or whatever. So you can see definitely how this could be helpful. All right, number 12. Okay, this is, like I said, this is typical of like an AP free response question. All of these, if you put A, B, C, and D, and like number 12, sort of as a D, would be a typical free response question on the AP test, where you're given this word problem, and then you basically have like 4 different things you have to do with that word problem. And the last one generally is more like theoretical, like what does this represent? Is generally the case. So let's see if we can tell what this would mean if we did this equation and we integrated it from 0 to 6. What would that mean? Okay, but think about in terms of what we're talking about. What does it mean in terms of coal mine? That's it. Yeah, so it does represent an area under a curve, right, from 0 to 6. But that curve represents the coal mine, sort of the rate of those coals mine.
They just give you a response right after that. It's just connected to
Yeah, so like I said, this should, I don't know why it's 12, this should be part D.
how.
I don't know, it's
That
connected
makes-
to that, yeah.
That makes sense.
Right. It's confusing to have it as a new question. It should be a part D. Yeah. So this represents the rates, right? This is a rate of change, okay? And then so if we integrate a rate of change, then we get an amount. And so the amount from 2000 to 2006. Amounts of coal mined year 2000. And make sure you don't say from year 0 to year 6. That would be incorrect. It's year 2000 to 2006. And then we get a table for the next one, so we're not done with this scenario yet. We get a table here, and this is the approximate number in thousands of tons per year. So this is 2,000 basically times 1,000. So that's 2,000 times 1,000 would give you a million. This is in thousands of tons. We're supposed to approximate the value of this integral using a couple different Riemann sums. So hopefully that's still a little bit fresh. We want to do a midpoint sum with 3 equal subdivisions. Let's do that first. With tables, I think it's easiest to just sort of pick out where your middle is going to be. This one, and this one are going to be your middle values, right? So let's think about how this works. When we do a Riemann sum, it's a rectangle, right? It's a length times a width, or sort of the width times a height, if you will. So we need our delta x. What's our delta x in each of these intervals? Yeah, 2. So each interval is really from here to here, right? From 0 to 2, from 2 to 4, and then from 4 to 6. And then so we're taking the middle of that. So the delta x is the same because it's equal, so we could even pull that out. So it's 2 times. And if you didn't pull that out, it's not a big deal. You could just do 2 times each one. But that's our delta x on each one. And then our heights are just going to be the midpoint values there. It's going to be 1837 plus 1549 plus 1307. So that's in thousands of tons. So that would be like 9,386,000. All right, and then we're also supposed to do a trapezoidal approximation with these widths as well. Widths of 1, 2, and 3 in that order. All right, do we remember how to do a trapezoidal sum? Just remember, think back like elementary, like what is the area of a trapezoid formula? Yeah. Times the height. 1/2 p1 plus 2 times height. If you know that, you can do the Riemann sum. Okay? If you just think back to that sort of elementary way of doing this. The 1/2 is going to be common in all of them because they're all going to have a half in them, so you can pull that out. Now the height, that is these widths. Yeah, it's a different word, but the height is the widths for each one. So the first one, I like to even write it first. It's going to have a width of 1. Okay, and then we have to average the two bases. So this is our first trapezoid here. 0 to 1, 0 to 1. So the average of the two is pretty obvious. 2,000 plus 1897. So that's our first trapezoid. And actually, rather than drawing it like that, I'm going to write it more like this. So our next trapezoid is going to be width of 2. So we're going to start where we left off. Yes. And then we're going to skip one because it has a width of 2. So plus 2 times, and then our two heights are the B1 to B2. So those are going to be the 1 value and the 3 value there. So 1837 plus 1549 plus, and the last one has a width of 3. So 1, 2, 3. It's going to be those are going to be our plus 2 times 1549 plus. And then when you're finished, make sure it's a number that's similar to the midpoint. If they're way off, then you can make a mistake. got 9,428. And then we got one more thing to do with this one, and that is to actually find the amount with our calculator. So how do we do that? Mm-hmm. And the function that we're going to use is the one that we wrote, right? The 2 million e to the negative 4052. And just when you write your answer, remember that we want to really drop off three of them, essentially. So that's into this one. It's 9 million. So when we compare it to the other two, it's really right in the middle, right? Because the other two, again, would be multiplied by 1,000, so we'd have 3 more zeros. So this is 9,400,104. 9,386. Everyone's able to type that in, okay? It's good to have answers that are consistent. All right. That's all of that. Let's move on to some more slope fields here. Let's take a minute to try these out. Also, before I forget, so probably what we'll do is tomorrow we'll finish this, and then you'll have the weekend to do your calculator section. Work. So let's find which of these is the solution curve. So this one's a little bit confusing. All of the slope fields look the same, right? They all look the same. So I would find 0 and -2 and figure out which one has the right sort of flow to it. There's definitely eliminate A, right? Because A crosses or it's undefined there. Right, right. I guess it's 0, so necessarily. So actually, that's yeah.
We could probably cross
No.
out C, because then we look at
D. Yeah. So yeah, let's cross out D or C. Yeah, it doesn't make sense because these are yeah. Because it would need to go back down to that. Yeah, and C doesn't go through the point. So it's either A or B. So they're the same except for this one spot, right?
I don't think it can be A because,
Because this road
well,
comes to.
Yeah, they're going that way.
yeah,
Yeah, so it can't be anything. So it's B is the only possibility. I'm not a big fan of these in general though, because it's just, I don't know. It seems too subjective.
yeah. I bet you can weasel in some sort of a weird answer that could sound right. Yeah.
Yeah, let's try 16. Which one has 3, 2?
Does this just say can read every
Mm-hmm.
the field? Some things.
They all go for 3, 2. I think this one's actually a little bit more obvious. So if you look at the differential equation, what can it not have? Can't have
Y
0 for y, right? Because it makes it undefined. And the only one, remember, sort of that rule is like basically if it's undefined, it just stops. So B is the only one that makes sense.
Yeah.
You definitely can't have D because that's not even a function. This one doesn't take into account the fact that it's undefined, like that. Yeah, it would just stop there. And C is actually a 0. So A or B would be your only options. But whenever it's undefined slope on the slope field, it just stops. All right, I think we'll stop there. We've got some actually limits to do tomorrow. It's like second fundamental theorem of calculus, extrema, maximum. Why don't you try these last two tonight? I'm not sure if we'll have time to get through everything. So do these two because they're kind of similar to what we did today. So we should have a lot of explanation.